In this video, we're going to talk about electromagnetic radiation and some of the major discoveries that led to the current model of the atom. So, one of the ways that energy travels through space is by waves moving at the speed of light. This is called electromagnetic radiation. So, the three main properties of a wave are the speed, which is the speed of light in an electromagnetic wave, the wavelength, which is the distance between two consecutive points on a wave, for example, the distance between two peaks or two troughs, and then the frequency, which is the number of waves or cycles that pass a given point per second. And the symbol for frequency is this letter nu, which is not the same V as in velocity. And the unit of frequency is hertz, which is just 1/seconds. So if we have a longer wavelength, then that means the frequency is lower. And if we have a shorter wavelength, that means the frequency is higher. So the wavelength and the frequency are inversely related. And so the relationship between them is given by this equation. For an electromagnetic wave, the wavelength times the frequency is going to be equal to the speed of light, c, which is about 3 times 10 to the 8th meters per second. So here are the different types of electromagnetic radiation, and they're classified based on their wavelengths. The shortest wavelength is the gamma radiation, and the longest is radio. And therefore, gamma is the highest frequency, and radio is the lowest frequency. So, a guy named Max Planck discovered that energy is quantized, and this means that it can only increase or decrease in certain increments. So, any change in energy can be represented by a whole number times the smallest increment, which is also called a quantum. So, for a change in energy, the quantum, or the smallest increment that it can change by, is given by h times the frequency, where h is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. So this is the quantum, or the smallest step that the energy can change by. So any change in energy will be an integer n multiplied by this quantum. So if we have blue light being emitted with a wavelength of 450 nanometers, then we can calculate the quantum, or the smallest increment of energy. So first we find the frequency of this radiation, which is the speed of light divided by the wavelength, so 6.66 times 10 to the 14th hertz. And then the smallest increment of energy, which is when n is equal to 1, is just h, Planck's constant, times the frequency. And so we get 4.41 times 10 to the negative 19th joules. So then Einstein suggested that electromagnetic radiation is quantized too, and it can be viewed as a stream of particles called photons. And the energy of each photon is just Planck's constant times the frequency of its radiation. And so we can also express this as h times c over the wavelength, because the frequency is equal to c over the wavelength. And he came to this conclusion by studying what's called the photoelectric effect, which is when you shine light upon a metal, it will sometimes emit electrons. So he found that only light above a certain frequency could cause electrons to be emitted. And if the light was below this threshold frequency, then no electrons would be ejected, no matter how intense or how long the light was shining. So this led him to believe that electromagnetic radiation had to be quantized, because the electrons are ejected when a single photon interacts with it, and it transfers energy from the photon to the electron, which causes it to jump out. So if each individual photon does not have enough energy, then the electron will never jump out, no matter how many photons hit it, because one photon has to have enough energy. Now, if radiation was not quantized, then the energy from the incoming light could basically add up, and eventually the electron would be emitted. But that was not the case. So Einstein also derived the famous equation E equals mc squared. So this shows that energy has some form of mass. It's not the regular mass that we think of. And so we can calculate the apparent mass of a proton by rearranging this equation to get the mass is equal to E over c squared. And then we know that the energy of a photon is equal to h times the frequency, or h times the speed of light over the wavelength. So if we plug this in for E, we get that the apparent mass of a photon is h over the wavelength times c. So electromagnetic radiation has mass since it has energy, and it can also be viewed as photons, which are individual particles. So previously it was thought to only be a wave, but now we can see that it actually has particle properties as well. So this phenomenon is known as the dual nature of light. It has both wave and particle properties. So if waves had particle properties, then it's likely that particles have wave properties also, which is what Louis de Broglie suggested. So if we use this equation with a particle that's not traveling at the speed of light, but instead at some velocity v, then the mass of that particle will be h over the wavelength times velocity. So if we rearrange this equation, then it should mean that any particle will actually have a wavelength too, even if we don't think of it as a wave. So to test this, people looked at something called a diffraction pattern. So diffraction is something that occurs when light is scattered by an array of points, such as the atoms in a crystal. So when light is directed at this crystal, then due to the way the waves of the scattered light behave, then it creates this unique pattern. So since this diffraction pattern can only happen because of the wave properties of the light coming in, then if we also shoot particles at this and it produces a diffraction pattern, that means the particles must have wave properties also. So that's what they did. They shot a beam of electrons, which were thought of as particles, at this crystal, and it produced a diffraction pattern, which meant that electrons had wave properties as well as particle properties. So when white light passes through a prism, then it produces a continuous spectrum, which contains all the colors of the rainbow. However, when the light emitted from a hydrogen atom is passed through a prism, instead of all the colors, it only produces a few lines of color. This is called a line spectrum, and each line corresponds to a particular wavelength. So it's not continuous. There are only a couple distinct wavelengths of light being emitted by the hydrogen. So this meant that the energy levels of the electrons in hydrogen, which were causing this light to be emitted, are actually quantized. So the electrons could only be at certain energy levels. So then Niels Bohr developed a new model for this hydrogen atom to account for the quantized energy levels of the electrons. So he proposed that the electron in the hydrogen moves around the nucleus in circular orbits, and only certain circular orbits are allowed. So then he found an expression to calculate the energy levels that the electron in hydrogen could inhabit, which is given by this equation, where Z is the nuclear charge, which is always 1 in the hydrogen, and N is any integer. So the lowest energy state would be when N is equal to 1, and we call this the ground state, the lowest energy state that an electron can be in. And so any level higher than N equals 1 would be higher in energy, and that's called an excited state. So when an electron drops from a higher to lower energy level, then the lost energy is emitted as a photon of light. So if we want to calculate the energy required to excite a hydrogen electron from the ground state where N equals 1 to an excited state where N equals 2, then we can just use this equation to find the energy at each level. So if we plug in N equals 1 and 2, then we get these two values, and the change in energy is simply the final energy at N equals 2 minus the initial energy in the ground state. So in going from level 1 to 2, it had to absorb energy, because we can see that the sign is positive. If it was negative, that would mean it released energy. And that happens when an electron moves from a higher to lower energy level. So this extra energy that it absorbed came from a photon. And so we can calculate the wavelength of the photon, because we know that the energy of a photon is h Planck's constant times the frequency, or in other words, h times c divided by the wavelength. So if we solve for the wavelength, then we get it's 1.216 times 10 to the negative 7th meters. And so it turns out that Bohr's model is actually completely wrong.